Yeah, so this is going to be a video about, let's say, programming and some methodology, and this is just for information. So this is just going to be a brief introduction to programming with some issues when it comes to programming. So we have a look here. There is a small presentation. This is what I talked about. So task at your hand. You get an assignment, and it's fuzzy, to say the least. It just looks like something like this, and it seems impossible to solve a task like this. So what you have to do is get a little nervous first, of course, but then you have to just grab the beast and try to do something with it. So what you should do is you should write a user requirement specification. The user, the software you're going to produce or write, what is it he needs, or what requirements does he have to set? How should it work? How should it be maintained, and so on? And then you have to write an FDS, function description, and/or detailed function description, where you describe how are you going to meet this user requirement specification. And then you have to break this down during this function description. You have to break this down into manageable tasks, subtasks. So here's the cloud, and you have to replace it with smaller clouds that you can handle, which are communicating with all these other small clouds. And this would be instances of classes doing program design. If you're not able to do this, and if you stay here and try to solve it in here, you are going to get a spaghetti program that's not going to be easy to work with at a later stage. You have to break it down in smaller classes or program units, or whatever you would call it. So what is good design or software design? It's easy to understand, it's easy to implement, which means to program it. It's easy to test it. Program that is not tested doesn't exist. It's easy to maintain and adapt changes, and as this is for automation, these changes can be in 10 years from now. 10 years after you have written the program, you should be able to retrieve the program, not you probably, but someone should, and understand what's going on. And then according to specification, of course. The specification would be then this, but then you will probably with your customer agree on this is how we're going to solve this. Okay, and then we are good to go. And then there is this UML that we have, Unified Modeling Language, where you can design your program. Here are some YouTube videos that you can look at. So that's an object-oriented system modeling of software components. When we are doing program, we are doing it in an object-oriented way, especially in automation, where we have real objects that valve and motors and analog measurements and whatnot, controllers. They are just objects they are working on. Well, a controller is, of course, a sensor and actuator, so there are two objects. And it's a standardized view of complex program. There are no UML products available for CFC program as far as I know. Might be now as of 2024, but we have a program in Codesys and TwinCAD, and also in TI Portal. We have something called continuous function chart, where you have these squares with interfaces. These are just the basic data types, binaries and so on, connected. They could be complex too, these types. You could use this as an UML tool. When you are designing your software, you can design it here. Just design the interface like you do here, but then you would have to write the code in here afterwards and provide the functionality for the interface. Breakdown. I'll look for repeating functionality, function blocks, classes, depending on your program. Look for low couplings, create classes and class hierarchies. So uncoupled, this is coupled, that's utopia. So if you have components that don't talk to each other, they probably shouldn't belong here. Low coupling, that's what you're looking at. High coupling, if there's high coupling between your components, maybe that should be just one component. Depends on the complexity. Then we have these coupled types. Uncoupled, no links between module. Data coupling, it's getting worse and worse down here. You can find this on the internet too. So I've just taken it as a stamp coupling. And that's where we call, when we look at the CFC up here, if you go back here, these could be complex data types. So that would be stamp coupling. They are then data must be identical in both of these components, or all the components using this data. To affect program execution, here you get, of course, this is not something you should do. Common coupling, common data source. This is use of global data, and that's frowned upon. Never use global data. You can, in a PLC, never use it. And when I say never, it means not never, but as long as you can avoid it, you should avoid it. And then content coupling, which means that a module is modifying, it's modified by another module. One module is modified, should say, read, cannot function without a modified module, and this is just bad design. You have this cohesion types. That's where you collect or aggregate your functionality. Functional, sequential, you have to aggregate and communicating. But for instance, use a resource that's common, so you just have to coordinate this, access this resource that you're using. Procedural, they have to be in order. If you make a sequence, for instance, they should probably, with more components in a sequence, it should probably be collected because they need to be executed. Also temporary. And then we have this logical. They are connected. Yeah, they naturally belong to, but they have no functionality dependence, and this random collect them just because I have to store this or collect it somewhere, make something, and just a mess in there. And that's what you call lazy engineering, and don't do that. And then a really important part here is what we call exception processing. When you make software, you have to handle exception. Exceptions are things that does not work as you planned for them to do. And they are going to happen. So that's affecting normal. Your programs should work like this, but something happens. You can't access a resource or something. Then all exception must be handled in a secure and consistent way. So if you have the same exception twice, you have to handle it in the same way. And it has to be a good way, a secure way at least. And here is a Windows exception, you know. Yeah. What to do here, I don't know. Typical exception here, that's not for PLC necessarily. A service can't be processed, but here are services, maybe access and output that you can't access, and you have to handle that, or you have to read access and input that you don't get. Wrong service, which of course we have wrong data, we have corrupt data. How to handle exceptions, retry several times. In PLCs, it doesn't work. There's no point in retrying it. Reset the system, the Swedish button. Swedes are not going to be happy about this. That's power on, off, power off. No, power off, power on. Or the way of resetting this, which is probably not an option in a control system. But at least then you have to bring your plant to a secure state before you do it. And then there's this abort and report. I can't do it. Report it. You can do this on control system, and the operator has to do some manual intervening, or I don't know, or something. And then there's tolerance to error. It's a system, your system built to produce a sensible reaction to an error, either in hardware or in software. Let us know what you're doing, and you will receive a hit for this. The latter, the software. So the hardware is probably something you bought, so that's not your problem, but your software working on the hardware, you have to be tolerant to hardware errors. Try to anticipate errors and try to build this into your software. Of course, in high-level language, you have these try-catch and finally and so on. For errors, for now, it's not in PLC program, might pop up at a later time. Yeah, so you have to arrange your hardware and software acceptable error reaction to these errors. That can be, for instance, a control system that we have an error in an input, and what we do is we bring our plant to a safe state. If there's a controller, we can't read the input anymore. We freeze the control signal, or we switch it off, or whatever is secure here. And then there's unhandled exceptions. There are exceptions that you haven't handled in high-level language. That's the first thing you do in high-level language. They say, okay, this in exceptions I don't handle, but I have to print a stack trace or whatever. I have to report. And then there's abort and report. In a safety and automation system, this is normally not an option that you have. Unhandled exceptions you can't have in a control system. You have to handle all the exceptions. But of course, they are simpler and it's possible to handle all the exceptions. If you have the IO, we need quality codes for inputs, and we have to handle those. Yeah, so that was about it. So this was a short introduction to what we called programming methodology, or what we would call it. And this is just for pure information. It's just some, let's say, somewhere you could, a clothes hanger for jacket or something, so you can put something on and try to have a look at it. So it's just for information, not comprehensive. But there are some, say, with the cohesion and so on. What else we would call it here? We had a breakdown to this USR and FDS and DFDS. That's important. You have to design and write what your software should do before you do any programming whatsoever. Yeah. And we do a little UML software. There's coupling types and there's cohesion. So we collect all the functionality classes and stuff for function that we need, depends upon what your program.